Hello, good morning, everyone. My name is Igor Giangrossi. I'm part of the consulting engineering team at Nokia working with mobile operators. And 5G is an interesting to talk about here because it looks like these days that you can talk about pretty much anything and relate somehow to 5G. But the idea here is to go through some of the requirements on IP networks, because before any radio can be deployed, before anybody can actually use their cell phones to use a 5G network, we need an IP infrastructure in place to interconnect everything. So that's the idea of the talk. Before we go into the technical part of it, I think it's nice to go through what is 5G. Well, that's a kind of hard thing to define because there's multiple ways of looking at the technology. Here you have a brief history of mobile networks, and you can probably tell your age by the first mobile phone you have. So we went all the way from analog phones that was basically circuit switched voice over radio. That's what it was. So analog radios doing voice calls. Believe it or not, it was made for voice calls at the beginning. And then we went all the way through the different generations. So 2G was all about digitizing the radio interface, so digital voice. It was actually the first time we got some data capabilities on mobile networks. Then 3G basically enhanced those data capabilities. We had the iPhone as the flagship cell phone of that generation. And then 4G further enhanced that with the notion that we didn't have actually circuit switched connections anymore. So 4G is actually the first mobile generation where we have an all IP network, so even voice runs on voice over IP. Now, we are in this phase where we need to transition between this 4G technology that we all use today, and it's good as long as you have good coverage, you can have pretty good service, and go to this new generation. So what does it look like, a 5G network? Many people think that 3GPP is actually the standards body that defines the generations, but it's actually not. It's actually ITU. So the ITU, every 10 years or so, works on the requirements for what's going to be the next generation of mobile networks. And you can see those spider web graphs here. You have on the left the requirements of the new technology, the 5G technology, and you see 5G does everything well. The gray area is the comparison with the 4G. So I'm not going to go through all of the elements here in this graph, but you can see some of the things that are widely advertised for 5G, such as lower latency. We're aiming at possibly a 1 millisecond latency end-to-end. Very high data rates, so both for peak data rates and maintained data rates. One of the important things when we talk about radio is the spectral efficiency. So spectral efficiency means how many bits you can crank into the same radio channel. That's essentially what it means, and we're obviously always trying to put more bits into the same spectrum. So in that sense, 5G aims to have a little bit around 3 times, 2.5 to 3 times more bits in the same spectrum when compared to 4G. And the big question is, what do you do with all of that, right? So what is the application? Is there a killer application? Is there a reason why you actually want all of these? So ITU went ahead and put the graph on the right, specifying the technology for 3 main use cases. And whenever you read this, even the standards for 5G, you're going to see all of those 3 use cases there. You see enhanced mobile broadband as one, which is very fast broadband. You see massive machine-type communications, or IoT. So basically, the ability to connect many more IoT devices in an easier manner in the network. And also low latency communications, ultra reliable and low latency. So that's another application. Now, before going into 5G, let's do a quick recap on 4G, because I realize many people here might not be aware of how a mobile network is laid out in terms of the main elements. So in a 4G network, you have the radio, which is called the E node B. So the E node B is what sits in the towers. Then that eNodeB is connected to two main elements. One is called the MME, the Mobility Management Entity. So Mobility Management Entity is the one who does the authentication, so it works with the subscriber database. It does all the mobility management, meaning that whenever you move between cells, it's the element that controls that mobility. And it also does a lot of session management. Session management meaning anytime you need to transmit something and establish flows across the network, it helps you set that up. Then we have the serving gateway. So the serving gateway is the mobility anchor point on a mobile network. So that means that whenever you move in a wide geographical area, you might change your serving gateway because that's what keeps the hierarchy to give you the ability to move around, basically. It does packet forwarding. It sits on the user plane, and it also participates on the session management. And the 4G core, as we say, it has a dual element approach for the user plane. So we have both the serving gateway, which is the mobility anchor, and the PDN gateway, which is actually the IP anchor. So that's, for folks who work with wireline, that's maybe similar to a BNG concept. So that's where you actually have your IP pools, you terminate your user sessions, and you interconnect to the internet. The EP gateway, the PDN gateway, is also the element that interfaces with a lot of adjacent systems in a mobile network, such as policy, charging, and so on and so forth. So there's a pretty complex control plane involved here to make sure everything works. Now, in terms of IP networking, what does that look like? So the network that interconnects all of these eNodeBs, all of those radios, to the core is typically known as the backhaul network, right? So whenever you hear backhaul, it's whatever is interconnecting the radios to the core. And here you have some of the protocol stacks that are used on those mobile networks. So for the control plane, there's an interface, and by the way, when 3GPP says interface, it's really a reference point. It's a kind of a protocol between two elements. That's what they mean by interface. It's not a physical interface or a port. So for the control plane, the mobile networks use IP and SCTP on top of it, with the control protocol being S1AP. So that's the control protocol that we have between the radios and the MMEs. And then for the user plane, we have GTPU, so GPRS tunneling protocol. So it's a UDP type encapsulation where the radio encapsulates all of the user traffic. So you see the IP in darker gray here. Those are the user frames get encapsulated into this GTP tunnel that goes all the way from the eNodeB, passes through the serving gateway, and ends at the P gateway. So the P gateway will remove that encapsulation, do all the subscriber management functions, and deliver the IP packet to the internet. Now, we also have a mixed controlling user plane traffic, which is called X2. So the X2 interface is actually meant for handoff. So whenever you're moving between different radios, you have to coordinate that movement across those radios, and also it serves to send some packets in the user plane while you're still doing movement. So there's a little bit of user plane on that, very quick, but mostly control plane for radio coordination. And that radio coordination, you see, it becomes very important when we go to denser environments. I'm going to talk about that later. The other element that I wanted to mention is that because mobile networks allow you to move between different radios, you actually need to have those radios synchronized. So there's synchronization going on between all of these radios, and you see here there's different methods for synchronizing those radios. Many of these radios use NTP actually for synchronization, but you can also use GPS. So GPS is very used. There's another technology that is widely deployed on many of these radios. But we can also use synchronous Ethernet or 1588 to synchronize these radios as well. So that is another requirement that typically we run through either through this backhaul network in terms of SyncKey or 1588 or NTP, or if you have GPS, typically you have one GPS per antenna or per tower. Now, when we look at 5G, this is the simplified view of a 5G core. 5G has some interesting concepts when it was designed. So one of the concepts was to have orthogonality of functions. meaning that every function or every node defined in the 5G core performs only one type of function or only one type of management inside the core. What that means is, for example, we have the AMF, which is the access and mobility management function. So that only does mobility management. If you compare, for example, with the MME in the 4G core, the MME did both mobility management and session management. Now, in the 5G core, session management is the responsibility of the SMF, so session management function. And those two elements are pretty much what we have in terms of control plane for a 5G core. The key characteristic of a 5G core is that it also came with a clear separation between control and user plane. So you see in the bottom, we have the radio, and by the way, it's called G node B, and the furthest I could try to understand why G, it's because it's new generation radio, so go figure. But the G node B, which is the radio, connects to only a single element in the user plane, which is called the UPF, user plane function. The biggest change with the 5G in terms of user plane is that apart from having a single element, and we don't have any more S gateway and P gateway, so we only have a user plane element. This user plane element can either be very distributed, so you can have your internet offload point closer to the user, being a content cache or even going directly to the internet, or you could have a centralized user plane as well. So that centralized user plane serves for more like centralized peering points. And you can actually have both. That's something new. Now you can have multiple IP anchor points across your network. You're only obviously going to announce your IP pools in one side, but it gives you the ability to install some, for example, content caches and do local breakout for specific applications closer to the user. I'm not going to go through that. If there's enough interest, we could even do another presentation on how that works. But the other characteristic that I think it's worth mentioning is that since we separated completely the user plane functions and the session management functions, that created an SDN type of scenario where the SMF acts just like a SDN controller to program the user plane functions that are actually forwarding packets. Right, so we have this N4 interface here, or N4 protocol, which I'm going to show you in the next slide. So basically what it's doing is the SMF, once it needs to set up some flows, somebody wants to access the internet for doing Facebook or whatever, it will go ahead and program those flows in the user plane function. So it's pretty much like an SDN type of environment. Now, how does the protocol stacks look like? So from a backhaul perspective, there's not a lot of changes comparing to 4G. There's actually no changes in terms of protocol stack because the user plane is still using GTPU. The control plane is still using SCTP. Obviously, there's a new control protocol there, which is called NGAP. And we still have that X interface. In this case, it's not X2 anymore, but it's XN between the different radios for better coordination and handoff. There are, though, a few differences here that you can start to see. One of them is that the control plane elements, in this case, the AMF, SMF, and as a matter of fact, any other control plane element in a 5G core, doesn't use GTPC or diameter anymore. So the two most used protocols in the control plane for 4G networks are diameter and GTPC, GTP control. So it's an extensible protocol for sending control information. 5G is now based on RESTful interfaces. So all of the 5G core elements that sit in the control plane, they can talk to each other using RESTful interfaces. And we also have a new model, which is called the services-based architecture, where we get rid of all these peer-to-peer or point-to-point interfaces between any two elements and create a kind of a buzz infrastructure in a publisher and consumer model where any of these functions can publish their own APIs and any other function can go ahead and consume those APIs as you need. So that is pretty good news because it facilitates reusability of all of these functions and makes standardization much easier. And then the other thing that I wanted to mention here is the N4 interface. As I mentioned, this is very much similar to an SDN type of scenario where the SMF programs flows in the UPF, and the protocol used for that is very similar to GTPC. So actually 3GPP looked at many control protocols for SDN as alternatives and finally decided to reuse GTPC and create something called the PFCP, it's Packet Forwarding Control Protocol. So basically what it does is it sends flow descriptors to the UPF, and with those flows descriptors it can send some specific actions to do with those flows, right? So very similar to what we already know as the concept of SDN. Now, is that all? So is it really just same thing as 4G and 5G, the same protocol stack? You know, you have some RESTful interfaces here and an SDN type of scenario. Well, that's not all. There is something that I'm sure you've heard it many times called network slicing. So the concept of slicing a network into virtual containers or virtual elements is not new for IP networks. We've been doing this forever, right? So with VLANs, with VRFs, or you pick and choose your technology for doing that. The difference here for network slicing in 5G is basically the sense that you get the slice now all the way from the cell phone to the core elements. So this means that the cell phone needs to be provisioned for using that slice. The radio needs to be provisioned for using that slice. You're going to need to provision your transport, obviously, because now you have some shared elements and some dedicated elements for each of these slices in the network. So there's a shared element called the NSSF. As the name implies, it's a network slice selection function. It facilitates, it helps slice selection for different connections. And the AMF, the access and mobility function, is the one who actually selects the slices for all of the users in conjunction with the NSSF. So that is a common element. But the whole concept of slices, which is to create a specific infrastructure to serve a set of UEs or a set of cell phones or terminals, demands that you might need to have some specific functions dedicated for that slice to provide some specific SLAs that are different across slices. So you might have a slice that demands some lower latency. You might have a slice that that demands some higher throughput, or a combination of both, and so on and so forth. And at the end of the day, what you end up with from an IP perspective, it's basically a classical traffic engineering problem, right? So you have some traffic flows that demand low latency, some traffic flows that demand higher throughput, maybe proximity is a factor. So you can think about all of these variables in terms of providing SLAs in an IP transport network, and that is nothing different than a traffic engineering problem, right? So you can actually pick and choose your own traffic engineering protocols to do that. You can do it, centralized with a PSAP. You can do segment routing. You can do MPLS-TE. So whatever protocol you know and you want to use there will be good. One thing that might be a little different as we move forward, and this is probably not something exclusive to 5G, but it's something that 5G will make bigger, or will make a scale much larger, is the fact that all of these elements that we see here, SMF, UPF, AMF, NSSF, and so on and so forth, they're not chassis, bespoke hardware. They're virtual elements. So in other words, they're going to be installed as either a VM or a container-based application sitting on a data center that needs to go through a fabric, needs to go through a data center interconnect. And then now what happens is that you need to extend that traffic engineering domain inside that data center environment. So that is a real problem that we need to solve. There's ways of doing it. But the biggest challenge here is that if you start building more distributed infrastructure in terms of the core to get closer to the user, that number of mini data centers will be much larger. And then cross-domain orchestration, not only across the data center, the physical network, but also the radio and the other core elements in a 5G network is going to be very key to realize this vision of a network slice or network as a service over 5G. Okay, so is this all that we got for 5G? Well, actually no, there's a little bit more to it, because when we look at building networks for mobile, for a mobile operator or for a radio, the radio is the customer, right? So we're actually building a dedicated infrastructure to serve this customer, which is the radio network that needs interconnection to the core. And there's lots of advances in terms of radio that we need to go through to fully understand the impact of 5G. So the key theme for deploying radio and mobile networks is densification. The reason why we keep getting all those new technologies and new generations is that we need more and more capacity and denser networks, or in other words, in a given area, put more bits, which will mean in some way putting more radios there. Now, if you start putting more radios into the same area, you need some sort of coordination. You need those radios to work together and not interfere with each other in such a way that it makes actually quality worse. So in those specific cases where you need dense radio networks, there was this concept of trying to centralize all the baseband processing into a specific node in a way that you can now actually better coordinate all of these radios out there, because they're all being processed from a single point and seen in the network as a single radio rather than different radios that need to communicate amongst them. So this led to an architecture that is called the CRAN, or centralized RAN, where you actually split that radio into two different elements. You have the RRH, which is called the remote radio head, and you have the BBU, which is the baseband unit. So for that to happen, we actually need a protocol in between, because basically what we're doing is splitting that radio into two different elements. And the protocol that was created for this is called CPRI, Common Public Radio Interface. So CPRI is a protocol that runs over a TDM infrastructure. And you can look at CPRI basically, you can think about it as radio samples over fiber. RF or over fiber, radio frequency over fiber, that's what it is. So it has a TDM framing where it sends some radio samples. You see here IQ data. It sends some control information when possibly you need to send some control frames to the radio head, need to reset that, and so on and so forth. And it also sends synchronization. So remember that I mentioned that the radio must be synchronized, so the antenna must be synchronized. Now you have the BBU being synchronized by something, probably GPS or NTP or whatever you have there. And you extend that synchronization link to the RRH. So because you're sending some digital radio samples and synchronization across this fiber, you have a very little tolerance for delay variation. And it's in the order of magnitude of a few nanoseconds. And the other characteristic is that because we are just sending radio samples, the amount of traffic in the CPRI interface is constant. It's a constant bit rate, regardless of the fact that if you have one user connected, 0 users, or 100 users connected to that antenna, it's always going to be the same bandwidth. So it's a constant bit rate, full of radio samples, and those radio samples are going to have user data or not, but they need to be there, and synchronization is there. So all of the deployments for CPRI today, they use some sort of optical multiplexing, either DWDM or CWDM, most likely CWDM, depending on the distances, but very likely CWDM. Now, when we take that concept and start to look at 5G, there are a few changes. And what are those changes? So in 4G, most of the radio channels that we use are typically 20 megahertz wide, right? So you might have typically 20 megahertz for downlink and plus 20 megahertz for uplink, or you could even have less than that, maybe 5 or 10 megahertz. But most typical networks will use something alongside those lines. In 4G networks, we typically use spectrum or airwaves that are closer to or under 3 gigahertz, so 2.5 gigahertz, 1.8, 2.1, 700. So there's many spectrum used across the world in different parts and different areas. And what happens is that in that area of the spectrum, which we can even say sub 6 gigahertz, we don't have a lot of space for channels. That's why we have 20 megahertz as typical maximum. Now, 5G changed that in the sense that it allows you to go with much wider channels, meaning that you can have up to 400 or even we're talking about 800 megahertz channels. So the wider the channel, obviously, the more bits you can put into it, right? So, and that's in those larger radio channels that you're going to be able to achieve the very high bandwidths that 5G promises. But there's one problem with that, is that those larger radio channels are only available in a different area of the spectrum. And that's why whenever we hear about 5G, we typically hear about millimeter wave. So millimeter wave are the areas of the spectrum that sit above 24 gigahertz. So what that means is that because we're now using a much higher frequency, we have a lot more space to put some bits there, but that signal propagates much less than the signals in the lower bands. So, which means that we're now going to need a lot more antennas to cover the same area if we need to work on that specific spectrum area. And the other technology that 5G brings to enhance the bandwidth is MIMO. So MIMO basically is the technique that allows you to send multiple times the same signal. It's going to reflect in different obstacles. And the cell phone is actually going to have multiple antennas and combine all of those signals to enhance the signal strength, or in technical terms, enhance the signal-to-noise ratio so that it can actually have better quality and higher throughputs. So if we take all of that and the promising speeds that we have, a 10 times increase compared to 4G, we start to see a little problem with CPRI. So the typical antenna in CPRI with a 20 megahertz channel will carry roughly 1 gigabits of traffic, 1 gigabits per second in that front haul link, right? So front haul is the area between the BBU and the RRH. So that front haul interface, that is this new area created by decentralization of processing of the radios, will have traffic dependent on the amount of channel wide or the width of the channel and the number of antennas. So if you have 1 gigabits per second for every antenna and 20 megahertz channel, if you start increasing the number of antennas, some 4G antennas have or 4G radios have 4 antennas, you can get to about 4 gigs. If you start putting MIMO on top of it, which is multiple antennas, like 64 antennas, and that is available today, you can possibly get to 64 gigs per second. But now if you go to 5G, which is looking at 100 megahertz channel or even 800 megahertz channel, you can go upwards of 300 or even further, 320 gigabits per second. Now, anything that you do, regardless of the technology you use, 320 gigabits per second is a very expensive technology, right? So it's not cheap. And if you think that you need to put one of these links to each and every radio in your network, you're suddenly going to realize that that's just not cost effective. That doesn't close the business case, right? So it's very apparent, and you can see that for 5G, we need to start changing the radio infrastructure for those denser deployments, because that CPRI interface, that front haul interface that exists today just doesn't fit 5G. Now, many standards bodies started looking at this problem, 3GPP being the main standards body that standardizes all of the technologies for 5G. But we also have other standards body looking at this problem. So one of them is IEEE. So IEEE came up with a standard called 802.1cm, or many call it by TSN, time-sensitive network. So that is a new standard for Ethernet-based type of front haul. I'm going to talk about it in a bit. And there's actually two other working groups at IEEE called the Next Generation Front Haul Interface, 1914.1, which looks at basically the requirements for front haul over packet networks, and 1914.3, which looks at how to encapsulate all of those CPRI radio signals into Ethernet, into packet-based networks as well. CPRI, which is actually a consortium of many companies, including Nokia, came up with a new specification for the protocol. So there's now eCPRI, which is Ethernet CPRI. As the name implies, how you transmit CPRI over an Ethernet link, and I'm going to show that you in a second. And there's also the MAF. The MAF, as it standardized the requirements for different types of traffic or different types of services over a packet network, a metro Ethernet network. It is also working on specifications for front haul. And there's many other standards body working on that, such as ORAN, that is looking at how to have interoperability of CPRI or eCPRI links. The Small Cell Forum is also working on some different things, and so on and so forth. So there's lots of activity in this area. Now, in order for us to address that problem with the front haul bandwidth, we need to look a little bit into the radio protocol split. So I'm not going to go through all of the details, but on the top here, you have the IP packet that you need to transmit to the cell phone. And in the bottom, you have the antenna, the physical antenna, the RF. And you have all of these protocols in between layer 1, layer 2 encapsulation, right? So the way we look at it is that as you move from the IP to the RF, your bandwidth increases. And why is that? Because you're getting actually more encapsulations and more redundancy, right? So you're actually trying to give you some protection for errors, for retransmissions, and so on and so forth. So as you move down the stack, you're going to have more bandwidth. But as you move down the stack, you also have a lower latency tolerance, right? Because if you look at an IP packet, what is the latency tolerance for an IP packet? It's anything, right? You can say, I don't know, seconds. But what is the latency tolerance for a clocking signal on a radio? It's very little, right? So once you get to the RF, your latency tolerance starts to be very little. So the way to look at it is that with the CPRI protocol, we're actually splitting the radio between the PHY layer and the RF. So that is possibly the worst place in terms of latency tolerance because it's the smallest latency tolerance. And possibly the worst place as well from a bandwidth perspective because you have all the encapsulations there already, right? So it's where you have the most bandwidth and the minimal latency tolerance. So the way 3GPP looked at it, and you see different options, those are the options that were studied, is actually with 5G, we now need a different approach. We need two different splits. We need a low layer split, which many times is referred to as a real-time split. And we have a higher layer split, which is sometimes referred as a non-real-time split. And the way it's done is such that everything now between the low layer and the high layer is, encompasses all the real-time functions of a radio. And everything on the top encompasses the non-real-time functions of the radio, right? So basically what we're trying to do is trying to get a better latency tolerance, a little less bandwidth in front haul, and also the ability to have a non-real-time element where we can deploy that more flexibly. So when we put that all together, we come to this architecture where actually a G node B, a 5G radio is actually now composed of three different elements, right? So we have now the RU, which is the radio unit. The RU has the RF layer, but it's also a little bit more intelligent than the typical remote radio head that we had in 4G because it has a little bit of the PHY processing on that radio unit. We have the DU, which is the distributed unit that does all the real-time processing of the radio. And now we have another unit, which is called the centralized unit, that does all the non-real-time processing of that radio. Now, because the CU processes things that are non-real-time, it allows you to actually use a virtual form factor. So we have a VM type of deployment, a virtualized type of deployment for that CU. And that's why many times when you look at the 5G radio, you think about it, or it's referred to as a cloud RAM. Because now you have some elements that can be installed in a cloud, right, in a virtualized form factor, and also some elements that are going to be physical or bespoke type chassis that process the real time. Now, if we take those three elements, we now have not only the backhaul, which you already had, and we talked about here. We had the front haul, which you already talked about as well, but we actually create a new area in the network called the mid-haul. And the mid-haul is what sits between the DU and the CU. So let's start to take a closer look at that. So the mid-haul interface, what is it? At the end of the day, the mid-haul protocol stacks are very, very similar, or actually the same as the backhaul. So you see the user plane is encapsulated in a GTPU, the control plane is encapsulated in SCTP, and you can actually have, it's optional, but you can actually have a separation of control in user plane for the CU, sorry. So if you do that, you actually have an additional extra control protocol, which is called E1, and the mid-haul interfaces are called F1 by 3GPP, right? So at the end of the day, mid-haul is nothing different, sorry, from front haul. The only really difference here is that the user plane packets are not IP, because remember, again, this is an intra-radio interface, and we have IP encapsulated into a PDCP protocol here in the user plane. But other than that, it's pretty much the same IP network, same IP requirements. It's good old IP networking, right? Now, what about front haul? So front haul in 5G uses the eCPRI protocol and not the CPRI anymore. So what is the eCPRI protocol? It's basically the adaptation of the CPRI protocol for using Ethernet networks. Now you have here the Ethernet network. I put there the Ether type. You can use VLANs. You can use 802.1p. So anything that you know and use today for Ethernet, it still applies for eCPRI. You have an optional IP layer with UDP. Many of the implementations are going to use IP because it's obviously much easier to remember and configure IP addresses than MAC addresses between many elements in the network. So IP is optional, but will probably be there. And then you have a single eCPRI protocol header. And this protocol header carries all the information that the CPRI protocol needs. So basically all the radio samples, which are user data, the real-time control, and some other services like, for example, remote access to the radio. If you want to update the software for the radio, you have a channel. If you want to reset the radio, you can do that, and so on and so forth. Now, one of the things that is different, and it's key to understand, is that eCPRI doesn't carry synchronization. If you remember, one of the key characteristics of CPRI is that it used to carry synchronization, and eCPRI doesn't. So whenever you do eCPRI front haul, we need to provide synchronization external to the CPRI protocol, and that is typically done through the typical packet-based or physical Ethernet type of synchronization, like SYNC and PTP. One thing that I wanted to mention is that the 5G radio uses a duplex type of technique, which is called TDD. So time duplex. And what it does is that instead of using a single chunk of spectrum or a channel for uplink and another channel for downlink, what happens is that you use a single chunk of spectrum and you split logically what you want to use for downlink and uplink. Because it's a time division duplex type of characteristic and not a frequency division duplex, you now need time and phase synchronization for 5G. So that is mandatory. In 4G, time and phase can be also mandatory if you use some specific techniques like TDOA for specific, increasing the precision on localization of users on location-based services. In the US, that is very much used. In Canada, it's not. For example, in other countries, it's not. You might get away with just frequency synchronization for 4G, but not for 5G. For 5G will require time and phase synchronization. Now, how is eCPRI better than CPRI? So this is a scenario assumptions that you have here, 100 megahertz and 8x4 MIMO and so on and so forth. I'm not going to go through all of the radio characteristics here. But when we compare that specific radio scenario, when we would have 236 gigs with a CPRI interface, an eCPRI interface will give us roughly 20 gigs in terms of user plane and 10 gigs, less than 10 gigs in terms of control plane, right? So you see a huge bandwidth reduction here by the order of magnitude of 10 times when comparing CPRI to eCPRI, apart from the fact that now eCPRI can be carried over a typical Ethernet link. Now, 20 is bigger than 10, right? So that means that when we use front haul interfaces for 5G, 25 gig E interfaces are going to be very common. And if you think about it, 25 gig E interfaces have been mostly used so far for server infrastructure and not for carrier infrastructure. So that's why whenever you think about Ethernet front haul, you better start thinking about how you're going to incorporate 5G Ethernet transport into your network, because 5G will require 25 gig interfaces, right? And this is specifically for the front haul. For the mid haul, for the time being, I think 10 gig is going to be good until we actually go to higher radio channels. And in that case, in millimeter wave, we might need some higher interfaces or higher than 10 gig. Now, what about latency? So I mentioned that latency is actually a key characteristic here because we're talking about intra-radio interfaces. So these are the values standardized by the eCPRI or recommended by eCPRI in 1914.1, and is actually mentioned in TSN 802.1cm as well. So from the RU and the DU perspective, you have a one-way latency of 100 microseconds, right? So that means that if you consider that a fiber, the light in the fiber travels at 5 microseconds per kilometer, that gives you around 20 kilometers from the DU to the RU. And I apologize, I'm from Canada, but it's about 12 miles if we convert that, right? So these latencies now start to have a very large impact on where we could place all of these elements in our network, right? Because if we have a radio tower, this means that if I'm going to use this DU and CU elements, a distributed radio architecture, my DU must be within 20 kilometers. And that 20 kilometers or that 100 microsecond needs to take into consideration not only the fiber, which is valid for both typical paths and also protected paths, especially if you use rings, but also for the latency introduced by any switching elements in the middle, right? So if you consider that maybe any switch with a few decent features will introduce roughly a few microseconds there, maybe 5 microseconds. For each of these switches that you put in the path, you're taking away 1 kilometer, basically, right? So you need to be very conscious of latency when you talk about front haul. Now, from the DU to the CU, it's a little bit more relaxed. It's in the range of 1 millisecond. That's the recommendation. And if you take that into consideration, again, that is going to translate into 200 kilometers. It's worth noting that this is the hard recommendations from the standards. Some radios might implement some more relaxed timing here. For example, we've been working with our radio guys to make sure that our radios can cope with a little bit more latency than this to allow for larger spans in terms of distances. But anyway, this is what's in the standards. And then you start to ask yourself, so hey Igor, you mentioned 1 millisecond latency end-to-end in the beginning. That was the goal. And you just said that the one-way latency here between the DU and CU is 1 millisecond. So how do you actually achieve 1 millisecond in 5G. So in order to achieve 1 millisecond in 5G, obviously you need a transport network that allows you to do that, right? You need spans short enough to be able to have 1 millisecond there. And you also need to place one of the user plane functions closer to that CU element and put the content right there. So in other words, you're only going to be able to achieve 1 millisecond latency in 5G if you have a very distributed content infrastructure, and if your transport network from the radio perspective allows that to happen in that latency time frame, right? Typically, that doesn't happen today, right? So all of the 5G or even 4G today core sites, they are very centralized, and that adds a lot of latency. So actually, the only way we're going to see reduced latency in 5G is when we actually realize that vision of going into the far edge and distributing content very closer to the users. And then you have the backhaul here with 10 milliseconds, so there's no hard requirement in terms of latency for the backhaul because it's now an interface that is outside of the radio, so it's not anymore an intra-radio interface. So you can just think about backhaul the way we've been thinking today. There's no hard requirements here. Now, 802.1cm, which was created by IEEE, the time-sensitive network standard, looks at the way in which you can actually use a front-haul link and mix that front-haul link with other types of traffic, because the greatest appeal of using Ethernet for front-haul is not only that you now get to use a packetized interface, but now you can actually reuse that fiber for other types of services to bring more revenue or whatever you need to do there, right? So whenever you do that, you need to make sure you have the right QoS policies in place to make sure that front haul works as expected. Now, 802.1cm looks at two profiles to do that, or two typical ways that we could do that. The first profile, it's called profile A, uses just strict priority, which any decent router or switch can do today. So we've been doing that forever. Which means that anytime you get a lower priority traffic, or actually a higher priority traffic, you transmit first, and lower priority traffic waits. So you have in your left the ingress queue, where you have gray with non-priority traffic and blue with the front haul traffic. So what it actually means is that you start transmitting your frames. If you receive a high priority frame, then you put it into the front of the queue, you transmit that, and then once that's empty, you transmit all the other frames, right? So we do that today. All of the equipments in place today, I would assume, support that. That's the case for sure for us. But 802.1cm introduces something interesting, which is actually valid for links that are 10 gig or lower. So it introduces the concept of frame preemption, which is something we have never done in Ethernet. And it's just a new concept where the idea here is to minimize jitter as much as possible. So the way you do that is you start transmitting whatever frame you have there, and the moment you receive a high priority frame, you actually stop transmitting that frame, you transmit the higher priority frame, and then once that's done, you resume transmitting the lower priority frame, right? So this applies to links that are 10 gig or less. And as you could imagine, this requires a change in the MAC processing, because now you have to stop transmitting some frames, you have to signal that, transmit another frame, and then resume transmitting the initial frame, and then rebuild that frame in the MAC chip. So if you want to deploy that type of frame preemption capability, you need a mated box. Both ends of the link need to support that. And you see some specific front haul products supporting that. But again, this only makes sense in lower speed links because the serialization delay is larger, right? So as you move into higher speed links, the serialization delay gets lower and lower, and then the jitter is just not affected anymore by strict priority. Now, synchronization. So I'd like to spend a couple of minutes talking about synchronization, because Remember that we're building this network to interconnect radios to the core. So the radio is really our customer here. And because the radio is our customer, the synchronization requirements are also driven by what the radio is doing. So if you're doing, you see in the table in the bottom here, the radio requirements, whenever you're doing basic radio features, just typical TDD, and you have some LTE coordination protocols there, you have an absolute time error of 1.1 microsecond from all the way from the grandmaster or the timing source to the RU, to the radio, right? So the timing error is the amount of error that is introduced in the synchronization signal all the way from the signal source to the consumer, right? So this is a pretty relaxed type of scenario where you have 1.1 microsecond. But as you go, and this is named category C, by the way, but so if you go do some more advanced scenarios like carrier aggregation, which is the technique where you use multiple carriers or multiple radios to serve a single cell phone. And if you do interband, that's two different radios in different bands. Intraband, it's two different radios in the same band, in the same spectrum. As you move across those more advanced features that require more coordination between these radios, the maximum admissible time error lowers. So your tolerance is lower. And you can see here that it becomes not only lower, but it becomes not more absolute all the way from the timing source to the consumer, to the destination, but now it's an error between any two radios that are serving the same cell phone, right? So in other words, it becomes a relative time error difference between two RUs, right? There's something else that we need to consider because this timing signal is going to be traversing routers, right? And these routers will introduce some time error in the signal. Now, there are some classes specified by the G8273.2 in terms of the maximum time error introduced by any given router. And you have here classes A, B, and C. So C is actually being standardized. Most of the routers sit in class A, which is plus minus 15 nanoseconds of error introduced. Many routers are now in class B, which only introduces 20 plus minus 20 nanoseconds. And some routers will come up with class C. So why is that important? That is important because now the number of hops that you can traverse all the way from the timing source to your destination is going to be a factor of, one, what you're doing with the radio in terms of requirements, and two, your capabilities of your routers. So that's what's going to limit the number of hops in your network for the timing signals, right? And all of this leads us to two different scenarios. So if you have a very relaxed type of time error budget, you're possibly going to deploy a centralized grandmaster with 1588, which is the protocol that provides us time and phase. Remember that 5G needs time and phase. So we're going to deploy a centralized grandmaster, and that grandmaster will serve the timing all the way to the DU and the RU, right? So the DU and the RU are the only elements in the radio that need to be synchronized. Remember that the CU doesn't perform real-time functions, so it doesn't need to have a synchronization signal or timing signal sent to it. Now, if you move to more strict type of scenarios where you have a more integrated functions between any given RUs, you might go to the scenario on the left with a more tight budget, where you put a GPS in the DU, and the DU actually becomes the grandmaster to the two RUs that it's serving, so that you can guarantee that that time error is going to be within bounds for both of these RUs connected there, right? And the way we do this is by implementing 8275.1, which is full timing support, meaning that every hop across the path is going to support timing, support boundary clock in terms of 1588, right? And we also recommend that we use sync key alongside that path. And the reason for using sync key is that sync key provides us with a very stable frequency base because it's a physical signal between Ethernet ports in different boxes. So with that specific stable sync key signal, we can build a very stable time and phase signal on top of it with 1588, right? So those two protocols work together to create a stable timing scenario. Now, to close, what does this all mean so far? Well, this all means that actually transport networks for 5G radios could become quite complex because there's no one-size-fits-all. So these are 4 typical deployment scenarios that we have in a 5G network. And you could have either the top one where you have the core, and then you have all 3 elements deployed in a very decentralized way. So you have the CU, the DU, and the RU. And in that case, you need to create a front haul, a mid haul, and a back haul network. Always remember that the CU will typically, the CU and the core will typically sit into a data center, right? Or if you possibly looking into millimeter wave, as we saw, is where you actually have lots of bandwidth. So you might want to combine the DU and the RU, because then you avoid having the front haul traffic, which is where the bandwidth is most intensive. And then for those millimeter wave scenarios, you only have mid haul and back haul. Or you can actually do some more centralized radio deployments where you have the CU and the DU combined, and you only have the RU in the field. And with this, you only need back haul, or only need front haul, but you always need back haul, right? And the last scenario in the bottom is kind of similar to the most typical distributed, fully distributed RAN, where you combine actually the CU, the RU, and the DU. So with that, you only have backhaul. You get rid of mid-haul and front haul. And it's very likely that if you have a network, you're going to have all of these scenarios together because you're going to be operating multiple spectrum areas, and all of these spectrum areas are going to require different radio strategies. So the summary here is that the 5G transport networks needs to be built hand in hand between the IP planning department and the radio department. There's no way around it, and very likely you need to support all of these, combination of all of these scenarios at the same time. So with that, I'll open for questions. I think we're a little bit over time here, but
Hi, Wes George with ByteGrid. 2 quick questions. One, is there a set of assumptions around all these different IP layer devices that they're going to run predominantly IPv6 only, given that you've got all of these different things that you say order of tens of thousands of towers with all of these different elements in them. Mm-hmm. There's simply not enough IP space, even if you're using private, to make that work. So was that an assumption from the beginning?
So the standards don't specify IPv4 or IPv6.
Okay.
If we, well, you can. I'm not going to go back because it's by just in the beginning, but because we use the GTP encapsulation on the user plane, you're actually separating the IP packets from the user from the infrastructure. So the infrastructure could be anything,
right, and
the user could be anything. Now, any best practice scenario that you might think about it, if you're building a network from scratch that's going to be that size, you might think about IPv6. The reality is that all of the operators already have some sort of IP infrastructure for their existing towers. Some are V6, some are V4.
Right.
So at the end of the day, there's nothing mandating V6, and operators are migrating to V6 as they move to, as their V4 infrastructure exhausts and they implement V6. So there's nothing mandated, but it's something everybody's doing.
Okay. My other question was relating to MTU. Mm-hmm. The internet sort of generally has this artificial limit on MTU, 1500, because of Ethernet. I was curious if there was anything in either the standard or sort of general design philosophy about what sort of MTU you're exposing as user payload, and then what that means in terms of the MTU you're designing for in the backhaul networks and in all these different elements, mm-hmm. Especially given that at the speeds we're talking about, I'm assuming serialization delay is less of an issue, but you were talking about strict priority and microsecond level latency, and so maybe that's not true. I was just curious if there was discussion on that.
Sure, that's a great question. The front haul actually asked for 2,000 bytes. So that's what's asked for a minimum in terms of the TSN, the 802.1cm MTU. Because obviously, as we saw, there's multiple encapsulations here. You mentioned that. So as a backhaul provider, you will want to have an MTU greater than 1500 in order to provide a 1500 MTU to the IP layer, which is deep inside all those encapsulations. So that really plays a role. And actually, there's lots of work done in mobile networks because you face different MTUs across the transport network and the radio and so on and so forth, and that directly affects the MTU that is sent to the user. So that is for sure something of consideration.
Thanks.
Not worry.
Rüdiger Volk, Deutsche Telekom. Well, okay. Essentially, I started with the same question as Wes. Let me follow up on that. Our experience over the years of actual vendor implementation and full feature equivalence between V4 and V6 used, and I think even still is in some corners a problem, is the expectation that everything that gets the 5G label and is sold actually will be able to fully work in V6?
There's no protocol specification in terms of V4 or V6 for 5G and the standards. Having said that,
the question is what is actually available in the market?
Right. So you can actually today in 4G, you can actually already get a V6 interface, right? So most operators do, especially for voice, for example, is very much used. So you can get both a V4 and V6. 5G is interesting because it also allows you V4 and V6. V4 is still there in 5G. So if somebody wants to keep using V4, you can. There's no mandate. Support, I think, for V6 from a packet port perspective and transport, I think we're pretty good nowadays. Obviously, the devil's in the details, and we need to take a look at that. But again, there's nothing saying you need to use V4 or V6. The thing that is different, though, that I didn't mention that's not in the context here is that actually 5G has Ethernet as a type of framing as well. So the idea of that is that you can actually, in the future, integrate other types of access that are not radio to a 5G core. That's just good to know. But I mean, V6 is going to be important for sure.
Yeah, well, okay. And talking about details with Ethernet, of course, the nasty details are, well, okay, you are not talking Ethernet, the DICS specification from 30 years ago. And you are talking 803. And it looks like very interesting to get 803 to do anything in MTU beyond 1500.
Yeah, for sure.
Jay Hannigan with Impulse. As you go to the millimeter wave frequencies, what is the effective distance or range from a handheld device that's changing its orientation so you can't really use any gain antennas? What density of cell sites are you going to need to support millimeter wave in terms of the range between the consumer radio and the serving cell site?
Sure, that's a great question. And the answer is a few hundred meters. So you can think that will only work in two scenarios for millimeter wave. The first scenario is that you're actually not using cell phones. You're using CPE devices with an antenna that is going to be put inside a home, and that antenna is going to be in the roof for fixed wireless. So that is one scenario that is going to be used. And the second scenario is it is actually possible to use cell phones, but it's with small cells. In indoor environments, for example, or stadium where you have very large density, so you want to put that small cell to serve a very small portion of people or very concentrated number of people in a given area. But we don't expect to have millimeter wave for consumer-based cell phone type of usage across a large geographical area.
Joe Hess Communications. We spent some time talking about this, and one of the things that came up in our little group was the possibility of having user caching. In other words, I have a set of cars on the freeway. Not all, they actually cache the information for other vehicles. Has this come up? Is there any provision in the standards for it, or do you think it would work?
Yeah, so there's some work on use cases for cellular to vehicle or vehicle to vehicle type of communications in 5G. That is part of the upcoming standard. So it's not being discussed now. So the current standards as it is, that is not included. It's much more in the concept of assisted information. So I don't think anybody expects that we will rely on a 5G link to take driving decisions in the road, right? So vehicles are going to be autonomous, and things like, you're 1 kilometer from a traffic light, or there's been an accident and maybe there's a fire truck coming, and things like that can be sent across the network. Now, when you talk about caching specifically, the only scenario where you could do that closer to the user is that scenario where I mentioned you must have a user plane function, a UPF, and the content sitting right behind that. So the closest you get is the closest any operator will deploy that user plane function. Today, those sites for subscriber management in most operators are very centralized. So maybe have a handful of those in most large operators. Then is a question of how aggressive the operators are going to be in terms of deploying that closer to the edge. I don't think it's realistic to expect that we're going to go from a very centralized architecture today to a fully distributed flip and a switch, right? But I think we'll eventually get there.
But what I think I just heard you say is that right now today, content distribution is a centralized function, and
Yep.
that's not likely to change. So if I were out there on the edge, I wouldn't be able to query other sites around me. I'd have to go back to the central controller, or it's the closest location of this content.
Yeah,
Thank you
that's
very
correct.
much. Good
Yeah,
presentation.
Thank you. Any more questions? Not, thank you very much.